Now, at some point, we will do, instead of regular classes, just question session, okay? So that means each of you ask question, and it's better if we don't do individually for the simple reason that in that manner others that might have similar doubts, learn from the answer I give to you. Okay, so I'll you talk to each other and schedule a day, but it has to be in the regular classes because I'm teaching at the university, so I don't have much time left. So it has to be during a regular class. So you look at the schedule and said, let's do tomorrow, let's do, you understand? Okay, so talk to each other and you let me know whenever you want a question session. It depends also when you finish reading the material and so on and so forth. I give to the guy Madi Torvayan, who will do the tutorials, the problem that we made, so that he can... Okay, so let's go on now. And we will continue with group and representation. I hope it's the right spelling. If I do English mistake, please do correct me because it's not my native language, so many of you representations. Okay, so we said which is the three properties that characterize groups. So it's a set of elements that have defined an operation in between the elements such that the result of this operation is still an element belonging to the group, and there is a neutral or identity element belonging to the group such that A times E is equal E times A and is equal A. And then to each element it exists an inverse element belonging to G such that A times A minus 1 is equal to A minus 1 times A is equal to the identity. These are the three properties. And examples of group, you see, this is the most used structure in physics nowadays. Well, actually, since the 50s already, it is the most used structure, actually, till the 30s. You have done quantum mechanics, so you study rotation group, the angular momentum, right, and so on and so forth. So there you have already seen. Nowadays, the mathematical structures that are most used are others, but this is part of the background that you should have. Have you ever done group theory somewhere in some other course? Have you done? The rotation, okay, but the general structure of group, no. Okay, so I will try to give a little bit, but not much. For example, let's take examples. For example, let's take this set. This is a set with two numbers. Let's see if we can give a group structure to it. Let's say that the multiplication is the usual multiplication among numbers, so 1 plus 1 is 1, so it seems at least 1 to respect this property that the product of two belongs to the same set. Minus 1 times minus 1 is 1, so it belongs to this. Minus 1 times 1 is minus 1. So if the operation, this operation, is the normal product, this is a group structure. That means all the operation that you do among two gives a third element that still belongs to the group. You see? Now let's see. So the first thing is verified. To every element belonging to G, to two elements belonging to G, A and B, it's possible to define an operation such that the operation between the two produce an element that still belongs to the same structure, to the same set. Okay, so that works. We have tried all possible, and the multiplication that we have defined is this. You can say, who defined the operation? Well, you define the operation. If you do things wrong, for example, if you don't do things properly, it has not the group structure. So for example, here we say it has this set, the group structure under the multiplication operation. If you instead introduce this other operation, under this operation, that has not the group structure. In fact, look, 1 plus minus 1 is 0, and it produces an element that it does not belong to this. So that set is not a group, it does not have a group structure under the operation of plus. It has the group structure under the operation of multiplication, okay? So let's see, well, we have not finished. So the first property is done. Second property, does it exist an element that is the identity? Well, 1 times 1 gives me 1, so this seems to be the identity, but let's try with minus 1. Minus 1 minus 1, 1 gives me minus 1, so the identity is 1. So we have identified, there is an identity element in this group. Third thing, is there an inverse? So, for example, to 1, do we have an inverse? Yes, is 1, because 1 plus 1, you know, the inverse is such that it gives the identity element. The identity element we have identified as 1. Let's see, minus 1. Minus 1, the identity, the inverse is minus 1. So this is not a group. You see? From here, we got the identity is 1. No, sorry. I thought this is 2. This is 3. So we have a group structure, okay? That means to 1, the inverse is 1, it produced the identity. To minus 1, the inverse is minus 1, it produced the identity, okay? So this has a group structure, but is what we call a discrete group. Why? Because it is made just of a finite number of elements, okay? Another, a finite number of elements, and that where the concept of closeness is not defined. Nobody here has told you if 1 is close to minus 1 or so. Let's do another example. The example is the one of all the real numbers. So 1, 1.1, 1.11 through to all the real numbers, positive and negative, okay? Of course, it has a group structure under the operation of dot. So the first property, let's take two real number, 3.2 dot 1.3 is equal, I don't know, 3 point something, okay? And this is a real number, okay? So second, there is the identity, yes, there is the identity, is 1, and in fact it gives me 1. Third property, there is the inverse, yes, 3.2 to the minus 1 is the inverse. So also the real numbers with as a group structure. You see how diffuse is this group structure, okay? You can, as I give you an homework, the set is U, okay? Invent an operation between you, like shaking hands, giving a punch or something like that, such that you have a group structure, okay? You can do any operation, I don't care. So let's see if you can find an operation that two human beings can do, like shaking hands, slapping on the face, or whatever, so that you have a group structure, okay? Don't be too violent or... Okay, another example. Let's take, for example, so let's cancel that. This is also a discrete set, you know, but is an infinite discrete set, okay? Let's take, for example, the natural number. So 1, 2, and only the positive one, 3, 4. These, and so on, all the natural number. And let's give as operation plus. Let's give as operation plus or minus, actually. Let's give as operation minus. Sorry. Let's give as operation minus, okay? Answer, but you should be able to give immediately. With this operation, this has a group structure? No, because of course, you know, you do 1 minus 2, you end up in an element that it does not belong to that. But if you put the positive and negative operation, then either with the plus or with the minus, this is a group structure. And so on. So you see how many of them you have. But the most important in physics, these are important in mathematics. The most important in physics are what are called, unfortunately in the note I did not write down this word, I realized only yesterday evening and I had already typed, is the concept of Lie groups. Lie groups from Sophus Lie. Sophus Lie was a mathematician of last century that study groups that have a concept of closeness. That means you can define, the problem is I need to introduce too many mathematical structures, so there is a concept in mathematics that is called topology. It tells you when two elements are close to each other. And there is the concept of continuity that you have done in calculus and so on. So Lie groups are group, but are continuous group. So that means elements in this group A prime, A second, and so on, can be parameterized by some parameter like the real number, so that all of these belong to a set that is parameterized by some parameter like epsilon, okay? And this epsilon can run, is a map into the real numbers. So if you have the concept of closeness or of continuity, so the set of elements makes a continuous, okay? And so it can make a manifold even. For example, those of the real one, the set of real number is a continuous group. And so the only property that when they say, is it a group? Yes. Then the next question you have to ask is a discrete group? That means there is a finite number of elements. If he says no, then you can ask, is it a Lie groups? Lie groups, if you don't remember the name of Lie, this is L-I-E. It means basically the set of objects that makes the group are close to each other, and you can define the concept of continuity. Okay. Now let's go and do an example so that the example that you have already done in quantum mechanics and in classical mechanics, that is the rotation. Okay, so let's see it in three-dimensional Euclidean space, labeled by x, y, z. And let's take as group elements, so the elements, let's call R, the element belonging to the group are the rotation along any axis that preserve this distance. Okay? So this is left invariant by any element R belonging to G. So let's simplify things. Let's do the rotation along Z. Okay? So rotation along Z. Let's indicate in this manner, just the rotation along Z. Let's see if it is a group. So now it is a rotation along Z, so it keeps invariant this quantity. Z does not change at all, and this is left invariant. Okay? So if you take a vector and rotate along Z, okay, Z does not change at all. So this does not change, and this is left invariant. Okay? So the characteristic of this group, sometimes you don't give the operation between one and the other. Sometimes you just say some property, but that property is enough to characterize, to say that there is a group structure. So we said, look, I take all elements that live invariant in Euclidean three-dimensional space, this distance, that is the distance from the origin. Okay? Now I will show to you that there is a group structure. Let's simplify things for the moment, and let's go to the rotation along Z. So if we do a rotation of an angle phi 1, and we do another rotation of an angle phi 2 along Z, so we do a rotation of a small angle, then of another angle, we know that this is a rotation of phi 1 plus phi 2, right? So it has a group structure. This is an abstract operation, means rotation. Question, there is the identity element? Yes, there is the identity element that is rotation by zero angle. Rotation by a zero angle, leave the rotation, so you do rotation by phi 1, then rotation by a zero angle, and you are left there. So this is the identity element. Is it clear? Okay, because I saw you looking. If you don't understand something, stop me, because I know I go to the speed of light, actually, a little bit more. And so please do stop me, because I need that. The students at the university know that very well with me. So stop me. Don't be ashamed of saying I don't understand. You know, it's better to say my things is it's better to say I don't understand in class where that at the exam. You understand my point? If you say I don't understand, okay, you cut a bad figure with some very smart guy who thinks he's Einstein and so on. And but it's much better if you cut a bad figure in class asking, can you repeat, I don't understand, or something like that, to do at the exam. Remember this rule. This is the rule that every student should have, also more senior people like me. And in fact, when I go to seminars, I understand nothing, so I can keep just asking. They are so specialized, I don't understand, so I don't go to seminars anymore. And just to tell you the story. That is, you will see, at my age, it will end up like that. But now that you are at the beginning, please do stop me with the most silly question, okay? I don't understand this. Okay, so first property of group is there. Second property is there. The third property is, does it exist an inverse? Yes. The rotation by the opposite angle. So if you do a rotation by phi and a rotation by minus phi, you get back to the identity, okay? So this is the identity. So it has a group structure. Let me tell you, not only the rotation along Z has a group structure. Please. You have to speak slowly and R, it means a rotation. Here. Is left invariant. Sorry. By R, by a rotation, belonging to G. Sorry, my handwriting is italics. Okay, so please. 2 pi, you get back to 0. Good question. So what happened is the group, that friend of yours just realized that there is these kind of things. So it means there is not a one-to-one correspondence between the real numbers and rotation. So if you take the real numbers, 0, pi, 2, pi, pi 4, and so on and so forth, the rotation is contained between 0 and 2 pi, and afterwards it is the same. Okay, so the correspondence is not one-to-one, but is one-to-many, and this has an important properties in the group structure representation. So now, if some of you wants to study group more in detail, an old book, there are many group books. You go to the library, you know, I imagine that this you have learned this year while you are here. Go to the library, you want to learn something about group, plug in group, and you see thousands of books, then you go and look at some of the book. But a good book that is an old book is Hammermesh. Hammer mesh. You will not have time in this course to, but if in the summer, if some other time, but next year when you enter the diploma or the PhD, whatever, I don't know what you do, you will have lectures on group theory. Okay, let's go on with this. This was rotation along Z, and you can say, yes, but a rotation is not just along Z. Yes, in fact, a general rotation, you know, a general rotation has this form. It is a rotation. So if you say, well, I take this table and throw it, it rotates, but it does not rotate along Z. Maybe sometime in moving, it does a rotation along Z, but otherwise it does a complicated rotation. You should have learned from Fabricesi, who did imagine classical mechanics, and I imagine he did it, that a generic rotation is a rotation along some unit vector, and the unit vector you just need two angles to characterize it. This angle phi, and this angle theta, by an angle alpha. So a generic rotation is always a rotation along an axis. Even if it seems very strange when you do a rotation, instantaneously it's always a rotation along an axis. That axis can change of an angle called alpha, okay? So to characterize a generic rotation, you need the two angles that characterize n. So n is characterized by two angles. N is a unit vector in any direction. And then the rotation is always a rotation along this direction of an angle alpha. Okay, so you need the direction, that is the unit vector. And why a unit vector, as is unit in length, I only need two angles, theta and phi, and then an angle along that things. So this is one of the most important, is what is called rigid dynamics, and engineers are very familiar with this, that any complicated rotation, instantaneously, if you look at it, imagine that you slow down the rotation or take a ralenti of that things like an athlete, and you see what it does. A table instantaneously is rotating along an axis pointing in some direction of a particular angle. That a fraction of a second after the angle, the axis has changed, so this n might have changed a second after, and the rotation on that might be beta. So immediately, so in general we say, well, this depends on t, the direction depends on t, and also this depends on t. That means it changes with time. So this is a generic rotation, okay? Now, I can prove to you, because this is a generic rotation, that also this has a group structure, okay? But I will not enter the detail, are quite cumbersome. You have to introduce the Euler angles and so on and so forth. Believe me, it has a group structure like a rotation along Z, okay? Now, this is a Lie group, because you see that you can do a rotation of an angle or of a smaller, an angle that is very close. So the concept of closeness or continuity there is for this rotation along Z, and there is for the rotation along any axis. So this is a Lie group. Sorry that I did not write down here Lie group, but it doesn't matter. I mean, you see, I don't know the final exam has, but mostly there might be a theoretical question beside a couple of problems or something. I don't know. I have to think about it. So, but I will never, I mean, you can say it is a famous mathematician. If you don't remember Lie, you will not be penalized, okay? Now let's see, for example, so this is, you see, this is abstract. I have not realized it in any manner. Now, let's go and see how we can realize, implement a rotation. Well, you know very well, if you write this as a vector, then a rotation is a 3 by 3 matrix that take this vector and rotate it, but it has the property, if this is a rotation, that the length is preserved. And this is the rotation group. In technical language, this is also called orthogonal group in 3 dimensions, O3. Orthogonal because it preserves this length, okay? There are more sophisticated things. Now, of course, you can say, well, this length is also preserved if you do this discrete transformation, or any combination of them. If you do this discrete transformation, is it included? If you don't want to include the discrete transformation, you put an S. It means spatial orthogonal group, okay? So this is the same as rotation in 3 dimensions. Of course, you know, according to the most modern theory, we don't live in 3 or 4 dimensions. We live in 11 dimensions, but the other 7 we don't see because they are rolled up or something like that. I'm not an expert on strings, so I can say a lot of rounding, but now, so that means you can go and have rotation in 4 dimensions, 5 dimensions, 10 dimensions. The only feature it has, so if you have a rotation, they say, what is a rotation in 11 dimensions? Is a transformation that keeps invariant this length that is the length in 11 dimensions. Okay? So a rotation in n dimension is a transformation that keeps invariant this length in 11 dimensions. Okay, good. Now let's go and see how these transformations are. And for example, we have done a transformation along Z. So let's go and see how this matrix R is. For example, let's take a rotation Z along Z of an angle phi, and let's see how is the transformation. The transformation is this matrix that is 3 by 3 as the following form: cosine phi minus sine phi, 0, 0, 1, sine phi, cosine phi, 0, 0. This is the matrix in 3 dimensions that represent the rotation along Z. Okay, you see, if this is the vector, it changes only x and y. Z is left invariant. Okay, so this is the representation in 3 dimensions of this abstract group. See, here we have not represented. We had not representation means we implement and realize with matrices, with something, how this acts. So we have to define the space in which it acts and so on and so forth. You want a rotation, for example, along x. A rotation along x must leave invariant x. So the rotation along x has a 1, 0, 0, 0, 0, and then we have cos phi, sin phi, along x, we said sin phi, cosine phi. Now, you want a rotation along y, it has to leave invariant y. So it has 0, 0, 0, 0. It leaves invariant y, and then you have cos phi, sin phi, minus sin phi, cos phi. Okay, so for example, this is, so rotation are realized here or represented, but only here, by 3 matrices. Now, in general, I said that the rotation as, this is rotation along Z, Y, but I can have a rotation along any direction. Sorry, I should not have cancelled. We have a 3 matrix that acts on this vector and produces another vector. It has the property that the length is left invariant. Okay, these are typical rotation. But now, if I want a rotation along not Z, Y, but as I said before, along a generic rotation. So I need to give 2 angles. I need to give, sorry, I told before, a generic rotation is a rotation along a unit vector of a quantity alpha. the unit vector you identify by two angles, theta and phi. So a generic rotation needs triangle, theta and phi. They find the direction, and then the angle of rotation along that direction. Now, how do I represent these things? Well, it is complicated. I will not enter it, but believe me, you have done, I think, this 3 by 3 matrix is represented in this manner. I alpha n times j, where this j, so n is the unit vector, alpha is the rotation along n. J are 3 by 3 matrices that you have seen when you did quantum mechanics. So this is a generic rotation along a direction n of an angle alpha, and the j, these 3j, are jx, jy, jz, and let's write them just for fun so that we have them, are Hermitian 3 by 3 matrix. But remember, I am doing rotation in 3 dimensions. I am not implementing the rotation group in the most abstract manner possible. I am just doing in 3 dimensions. You can say, well, rotation can be also in higher dimension and so on, and even if you stay in 3 dimensions, it can have different representations. So now these 3 by 3 matrix, so this is a generic rotation. The 3 by 3 matrix are the following: 0, 0, 0, 0, 0, I, 0, I, 0, then 0, 0, I, 0, 0, 0, minus I, 0, 0, and 0, minus I, 0, I, 0, 0, 0, 0, 0. You see the matrices are Hermitian matrix. If the angle is small, then you can do a Taylor expansion and you get 1 minus alpha n times j n. I put a hat. A hat, it means it's an operator. It means like a matrix. A vector, it means it's more than 1. So there are 3 and there are these. Okay? Now, these objects are also called, you know, from quantum mechanics, generator of the transformation. Why generator? Because you just need these. Once the direction and the angle of rotation is given, you just need these 3 objects. And you see, these 3 objects are the same for any rotation. They are universal for any rotation. What changed for the rotation is this part, but the matrices are the same. These generators are very important because you can ask me, now, if I do a rotation along n by an angle alpha, and then I do another rotation, you told me that, I told you that it's a group structure, so the next question is, if I have a rotation along n of an angle alpha times a rotation along m by an angle beta, question, this must be a rotation along some direction that I don't know which one, let's call L, no, let's call P, of an angle gamma, okay? But I need to find, this one I give to you, I need to find out this. Well, this is a complicated thing, but it's all based, you see here, this change, but the j are the same. Here, this change, but the j are the same. Here, p change, gamma change with respect to that, but the j are the same. Now, to find out this number, that means the composition rule of that group, you just need the algebra of these 3. That means the generator that we call jx, jy, and so on, we just need to know how they commute among each other, because this object is built, this object is something I, blah, 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 and then there are the commutator between the various ji, jj. Okay? I don't give you the detailed structure. I don't remember actually by heart, But it is this one, when you do the composition of two rotation, you get the commutators, or the commutators of the commutators. So what happens is that you know that the relation is I, J, Z, and the cyclic one, right? This is called algebra of the generators. Now, an algebra is not a group, but is one of the structures that you can give to a set. So here is a set of 3 elements. The operation I introduced is the one of commutator, and it has not the structure of a group, it has the structure of an algebra. A structure of an algebra is more complicated than group. It has 2 operations in it, okay? There is this operation, and there is also the operation of multiplication by real numbers, okay? So this is the algebra of the generator, and from this you build the group, or you build the group in this manner. You take R, and you do exponential I, N, alpha, J, and you see everything is okay. And you see, so from the algebra of the generator, you get the group structure. So instead of going around with the infinite set of the group elements, there are many, you can do any rotation along any things, it's much better to go around with the generators. You put in the pocket the generator, you look at it, and immediately people say, oh, these are the generator, they make an algebra, but the group associated is the rotation group. From the algebra, you see immediately which is the group. You understand? So this is a much smaller set of information that tells you everything, because here, for example, instead of having this, I could have, for example, plus I, Jx. This is a different algebra. Instead, I know that I have this structure. For which group? For the rotation group. So the algebra of a group, of a Lie groups, is a very important concept. Why? Because it is a much more, you don't have to go around with these matrices and so on and so forth, remembering by heart these matrices. No, no, it's enough to have this algebra of the generator, or that they commute among each other, to know which group they make up. And they make up that group by exponentiating. This is exponential alpha n j, okay? So the algebra associated to a Lie group, the algebra of the generator associated to the Lie group, is a much more compact set of information that you need instead of carrying around the infinite set of elements of the group, okay? So remember, there is a close, a one-to-one relation between the algebra of the generators and the group. So the algebra is, there is a one-to-one relation between the algebra and the group. So Lie groups, there is a one-to-one associated with the algebra of the generators. That means Ji, Jj is equal to some function of J, k. Okay, we don't know the function, but the algebra anyhow close on itself. And how many generators are associated to an algebra? There is one-to-one relation. It depends how many parameters you need for the group. How many parameters we needed for the group? We needed 3 parameters, right? The 2 angle for theta and the angle around. So there are as many generators as parameters. Of the group. Now let's study a little bit the algebra of the rotation group, and let's see. Now I repeat what you call the angular momentum quantization. In quantum mechanics, you saw angular momentum quantization. And now the same argument, we will go through the same argument, but it's called representation of the rotation group. So now this is what you already know. Now I will show to you that in group theory language, this means representation of a group. Now let's start with the Jx, the rotation group, I, J, Z. Let's forget that these we represented before as 3 by 3 matrices, this generator we wrote down here. Let's forget about it and let's suppose we have only this group structure, this algebra of the generator. We know that via the algebra we can build the generic abstract group composition law. Let's see one question we can ask. As we stay so abstract, we don't represent by 3 by 3. There are other representations. That means beside 3 by 3 matrix representing rotation, there are other structures like 4 by 4 matrix, 2 by 2 matrix, 6 by 6 matrix that have the same composition law, so that from the abstract point of view, they are always rotation group. Okay? So let's stay general and let's see how we do. You know what happened. There is an object defined in this manner that commute with all the generator. Okay? This object, you said total angular momentum square. In this language, this is called Casimir operator. So I just tell you the difference in things. And then as it commutes with all 3 of them, you can diagonalize it. And you know, let's take h bar to 0. You can diagonalize this operator. It commutes with all of them. You have done this in a classical thing. And they say J is an integer or half integer. M goes between J and minus J. Right? This is what you got from all that set of operation. Remember, introduce the J plus, J minus, and so on and so forth. And you see that this is very general. It does not tell me that J is 3. Right? In fact, you have the spin. This is the same algebra, but J is 2. So this is the Casimir operator. Now, for example, let's take J equal 1. Then if J is equal 1, M can be 1, 0, minus 1. So we have 3-dimensional state. We have 1, 1, 1, 0, 1, minus 1. So our Hilbert space is 3 by 3. And the matrix that represents the rotation will be matrix 3 by 3. So how we recover the 3-dimensional representation that we had before? Choosing J equal 1. But the general theory tells me that J can be also another thing. So this is called vector representation of the group. Okay. Then, as the general structure tells me, look, I can have also J can be integer or half integer, so J can be equal 1/2. Then M can be 1/2 or minus 1/2. Then the states are 1/2 minus 1/2, 1/2 plus 1/2. So the Hilbert space is 2-dimensional, and the J will be 2 by 2-dimensional matrix. So this is a 2-dimensional representation of the rotation group. And you can say, oh, but rotation is only in 3 dimensions. Yes, it's only in 3 dimensions, but is only in 3 dimensions if you see it as x, y, z. That is already a representation, okay? So here, it's not that am I doing rotation in 2 dimensions? No, because rotation in 2 dimensions does not need 3 generators. Rotation in 2 dimensions, that is around z, for example, you do the rotation in x, y. Okay, that is, it needs just 1 parameter, so not 3. So this, even if it has it is in 2 dimensions, this abstract space, but it's still rotation in 3 dimensions. That means it's always O3, okay? Note this. When I say, look, what is this? Many people have answered in written question, at least at the university, oh, this is rotation in 2 dimensions. No, this is rotation in 3 dimensions, but represented in this smaller space. That is not space-time, it's an abstract space. This is not space-time, it's an abstract space, okay? And so on, then you can choose j equal 3/2, then m can be 3/2, 1/2, minus 1/2, minus 3/2. So the states are 3/2, 3/2, 3/2, 1/2, 3/2, minus 1/2, 3/2, minus 3/2. So this is a 4-dimensional space. It does not mean, this does not mean it keep invariant something like this in 4 dimensions plus an extra, let's call t. No, 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 no. This is rotation in 3 dimensions, represented in an abstract manner in an Hilbert space that has 4 dimensions. You see, this, I want that this is very clear, and I stress in the pages, but I did not want to, you know, be... So, it's for that people don't talk about rotation in 3 dimensions. They say, let's take this abstract group. This is a group that has 3 parameters, and that in 3 dimensions keep invariant a length. But you can, this is the group. Then you can have the representation. And you can represent this in many different Hilbert space. In 2 dimensions, in 3 dimensions, in 4 dimensions. Then after 3/2, what do we have? What? What? I go to Thomson and tell, oh sorry. I go to Thomson and tell that you have to redo quantum mechanics. All of you failed, okay? After 3/2, what do you have? Did I hear right 5/2? 2 you have. So, this is terrible, huh? So, these correspond to 1/2, this correspond to 1, j. This correspond to 3/2, j. Then I have 2, and how many I have? How many dimension? How many dimension? 6. You have 2j plus 1, 4, 5, sorry. I also should redo quantum mechanics. So. Don't tell Thomson, okay? Okay, and you go on like that. You see, this is representation in a different space. I am not representing it in space-time. I am representing in a different space. But, you know that this state, you can go on then and represent in this space. And then you will have function of x, y, z that are function of x, y, z. The transformation keep invariant the length, but they are not the usual things. For example, the one you have done the spherical harmonics. The spherical harmonics are these sandwich on x, y, z, x, y, z, x, y, z. So I took in Hilbert space of the group this representation, and then I projected on this space. So if you want to have a contact with the normal space-time, you have to then represent this on this space. But you see, again, Okay, I don't want to insist more, but the concept of representation is a more abstract concept because it's not represented in space-time, it's represented in a Hilbert space, and the dimension of that Hilbert space is dictated by the algebra, because you remember that these came out of the algebra, that this number could be an integer or an alpha. So everything is embedded in this. That is why, you know, if we have to communicate with some exoplanets, inhabitants of some exoplanets on some galaxy, we will not explain all these to tell them the rotation group, okay? Maybe they have difficulties because maybe they are beings that are like boxes, not like us, and so they only know discrete transformation of 90 degrees and they move like that, okay? So, but you know what we do? I mean, here, we send to them not all these words that I explained, we send to them this. And then let them think, okay? And well, over the centuries, they will develop. Maybe they already did 3,000 years before we did. But then they will realize, aha, these are the rotation like if we were a sphere and so on and so forth. You understand? This is the smallest information that contains all the rest, if you are able to develop. All the rest are theorems. So you give only the basic element, the postulate, or the basic structure. So the basic structure is the algebra, okay? So let me make a scheme. Let me make a scheme because now we will go to the most difficult part, that is the Lorentz group. So we have a Lie group with element belonging to a group. Lie group in the sense that an element, let's say R, belonging to a group, associated to a group that is... Please, do. The most stupid question will get the highest grade, so please, ask a very silly question, okay? Yes, that's a good question. Right. You know, the point is the following. You need a Casimir because as it commutes with all of them, you can diagonalize immediately and associate the eigenvalue. You don't want to go around with big operators and so on and so forth. You want to go around with a string of numbers. So you choose an operator that commutes with all the other. You can diagonalize it, and then you have the string of eigenvalue. You understand? So you always need to find how many Casimir are associated to an algebra. So, okay? There might be many. That is called the rank of the algebra. For example, for the rotation group, you have one Casimir. Okay? We will see that for the Lorentz, we have two. The number of generators are more for the Lorentz. We will get there today or next class. So, associated to the Lie group, there is an algebra of generator. Then the group element is E alpha I Ji, sum over Ji. These J are not necessarily the rotation group. You see here I put a function f, and this I can go from 1 to m. So I'm staying with the generic Lie group, okay? So here I put a function. So this is a generic Lie group. You always have this structure, that there are the generator. The generator, why are they important? They are important, maybe I should actually put this before, that a group element can always be written exponential alpha I Ji. So a Lie group can always be written in this manner, where the Ji satisfies some algebra. Okay? Out of this algebra, you build the Casimir, find the Casimir. Let's call the Casimir, they have a name, they are called C. Find the Casimir operator. They are C of Ji, Jj, jk such that c and ji commutes. This is the Casimir operator. The third step, so first you give me the Lie groups. You can write in this manner. Second, find the algebra of generator. Third, find the Casimir. Fourth, diagonalize the Casimir. So C on some Hilbert space is equal to some number, let's call CK, and so on. And this is the Hilbert space which carry, of course you have CK, CK, and then other numbers, is the space which carries the representation of the group. Okay. So this is what you do. And now you are representing the group in this abstract Hilbert space. Yeah, take some notes because I did not write all the details, but in the question session you please do ask me whatever you don't understand from both my handwriting and from the thing. Okay, so let's keep in mind this general structure, and now let's go back to the rotation group as an example. Can I cancel? 4. When I can cancel, please, you let me know. There I can cancel. Okay. The rotation group will be our prototype group because you have done in quantum mechanics and so on. So rotation group is the one that keep invariant these in 3 dimensions. And the algebra is Jx, Jy equal I, Jz. In 3 dimensions, I have the representation that you have seen before. So in vector representation with Jx equals 0, 0, 0, 0, 0, minus I, 0, I, 0, Jy. This is a vector representation, so 3-dimensional representation is only one among many. You have seen the things. 0, 0, I, 0, 0, 0, minus 1, 0, 0, and Jz is equal 0 minus I, 0, 0. This is not the only manner to represent these 3 methods, but if you check, do check, because I might have done a mistake, they have the algebra written there. So this is our prototype group. Now let's go to the Lorentz group. Let's consider Lorentz group not just the group of transformation of velocity that send a frame from 0 velocity to 3 velocity, but let's stay more general and as close as possible to that structure. So this is the rotation group. Let's do the Lorentz group, and we define it as the, this rotation group is also indicated as SO3. 3 does not mean X, Y, Z. No, it means it has 3 parameters. Okay, remember this. This is the orthogonal, all the matrices labeled by 3 parameters, okay, and are the orthogonal matrix, and you know that how is defined orthogonal matrices. And thus it means we don't have discrete things. So we call rotation group because one of the representation of SO3 is exactly the rotation in 3 dimensions, okay? But it's only one of the representation. This group is much more abstract. If you go and talk to a mathematician, some of the mathematicians don't even know that this represents the rotation group. For them, it's one group, and they do the representation, all abstract things. They never tell the students. I mean, at least I see many students in mathematics in their 3rd year that, I don't know here, but in many places I have seen that they handle that in an abstract manner. Now, the Lorentz group. The Lorentz group is indicated as O31 formally. It means the following. It means the following. Let's go to a particular representation. So here we have gone 3-dimensional representation, just to exemplify something of the abstract rotation group. We choose this representation just so that you have a better idea. The Lorentz group is abstract group indicated in this manner. What does it mean, O31? It means it leaves invariant the following things: ct square minus x square, y square minus z square. This is, let's call delta S, okay? This is the quantity that is left invariant. So we call Lorentz group that group of transformation that leaves invariant this. Now the 3, 1, it means there are 3 minus 1 and 1 plus 1. So this is a pseudo length. In my notes already is a pseudo length because they are not plus, plus, plus. Okay, like normal length. Look, normal length. X plus y square plus z square. Here is a pseudo length because I have some minus sign. And this 3, 1, it means I have these keep invariant length that are built out of 3 minus 1 and the plus 1, okay? So that this is the same, it means you do a transformation and this quantity does not change. You see, it's the analog of this. Like rotation, keep invariant this quantity is the same as x prime square, y prime square plus z prime square, okay? Rotation, keep invariant the length. Let's call Lorentz group not just what we talk up to now, that is the transformation, the boost transformation, the one from 0 velocity to, no, let's call it the one that keep invariant this. Then, if this is the most general, please. No, we need 6. You will get in a moment. I was getting there. So this needs 6 parameters, and I will show to you why. Remember, it's not anymore the change in velocity. If it were the change in velocity, we just need 3, because to change a velocity in 3 directions, you need 3. But we said, look, the Lorentz group is more general. It's the one that leaves invariant this. Oh, then I have a transformation like the following. We are in 4 dimensions. Yes. Let's do the following transformation. A 4x4 matrix, where here I put a rotation. This transformation leaves T invariant. This one leaves this invariant, so it's a Lorentz transformation, right? This particular rotation that I represent in 4 dimensions, putting a 1 there, so this is a Lorentz transformation associated to the rotation. So a Lorentz associated to the rotation. What it does, it sends T into T, and it sends x into x prime, y into y prime, z into z prime. By what? A rotation. Do they keep invariant this? Yes. T is left invariant, and this is left invariant by rotation. So if the Lorentz group is that, here I have already 3 parameters. 3 parameters of rotation. Now these I can parameterize as I did before, right? As I did before, so what you need is just always have a 1 here, and here you can put as generator one of these 3, right? So basically the generator, so 3 parameter of rotation plus, we will go and see. So rotation for sure are a subgroup of the Lorentz group. They live invariant this pseudo 4 length. Now we have another transformation we have studied before, that is the boost transformation. The transformation, the Lorentz transformation. And if you remember, the Lorentz transformation was done in the following manner. Okay. You remember that we did, we said, well, like the rotation, you use cosine and sine. For the Lorentz, you need the cosine hyperbolic and sine hyperbolic. So let's call a Lorentz transformation that changes the velocity along x, for example. And you know, let's stay in 4 dimensions. It is cosine hyperbolic psi x, sine hyperbolic psi x, 0, 0, sine hyperbolic cx, cosine hyperbolic cx, 0, 0, then you have 0, 0, 1, 0, 0, 0, 0, 1. This is a boost in the x direction. Why is not a rotation? Because I use the cosine hyperbolic, and I have shown to you in one of the other lectures that the cosine hyperbolic of some quantity related to the velocity, v over c, and so on, remember the relation, is a boost, is a change in velocity. So this is, for example, a boost along x. Let's write a boost along y. A boost along y is again a cosine hyperbolic things, cosine hyperbolic say y, 0, sine hyperbolic set y, 0, 0, 1, 0, 0, sine hyperbolic cy, 0, cosine hyperbolic cy, 0, 0, 0, 0, 1. This is a boost in the y direction. Okay? I did not write down do as an homework, but think about it, okay? Don't take just because I said. I mean, you take what he says only from God, not from me. Okay, sorry. So, these things. So please, this is clear that, you know, remember this is t, x, y, z. So it always, the boost always changes t and x if it is along x. Here, tau, x, y, z, or t, sorry, not tau. Otherwise we confuse with t. Here, what does it change? Look, it changed t and y, right? In fact, the Lorentz transformation of a boost along y is this. Third, you have the one along z. So L along CZ, it will change always t. X, y, it does not change, it will change z. So you have cosine hyperbolic CZ, 0, 0, sine hyperbolic CZ, 0, 1, 0, 0, 0, 0, 1, 0, sine hyperbolic CZ, 0, 0, cosine hyperbolic CZ. Okay? So this is, in 4 dimensions, the representation of the Lorentz group. Keep as a prototype the rotation group. You see, it is a sort of rotation, pseudo-rotation, because there is a minus, in 4 dimensions. But that is just one representation. Remember, like for the group, there are many. Okay, the Lorentz group keep this invariant. This is a representation. We have found that there are rotation inside and there are boosts. How many boosts do we have? 3. So these are on the notes, okay? So I can cancel. You find in the notes that I'll send after the class to your classmate. plus 3 parameters for the boost. As we have a group, we have a Lie algebra. And the algebra, how many are the generators? 3 or 6? 6, because we have 6 parameters. So we have to find 6 generators. Well, 3 are the usual Jx, Jy, and Jz. The other 3 related to the boost, we call K. We call K, Kx, Ky, Kz. Now, as I give to you the, and remember, by the way, an element here is exponential I alpha times n times Ji. A transformation here that I called, how did I call before? L. So this is a rotation in 3 dimensions, in 4 dimensions because it leaves T invariant. The generator instead here can be written in this manner. Beta M K. Note there is no I. Why? Remember that you use the cosine hyperbolic? So if one has the I, the other does not have the I. But look at that. How are these K? We represented this in this manner, like the rotation. Now we are in 4 dimensions, we only have to add a 1, 0, 0, 1, 0, 0. How are the K? The K can be obtained. Go back to your quantum mechanics and see how you obtain this. Go back and see how you obtain this. You obtain this in this manner. You took Jx and sandwich between Jm, Jm prime. This is how you obtain these elements. You remember? Go back and see that. Then you transform Jx in J plus and J minus. You see how they act on Jm and so on and so forth, and you go on. And then you get these elements. So these are obtained in this manner. The same we can obtain for the K. And the K have the following structure. Kx is equal 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Ky is 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. And Kz, also this you don't have to copy. Also this is on the notes. 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0. Okay? Okay, so this is the representation of the generators in 4 dimensions. That is the smallest dimension? We will see. Is 4 the smallest dimension? We will see. But it's just a representation. What you can ask me now is, well, look, you gave me the algebra. You said to that habitants on the exoplanets, you just send the algebra because out of the algebra you build the group and so on and so forth. Which is the algebra of this? Well, the algebra of this, because I have 6 things. The algebra of this is the following. Ja, jk is equal I, epsilon I, jk, sorry, jj, jk, sum over k. This is for the j. Then I need the algebra between the k. And the algebra between the k is chi I, chi j. You combine 2 boost rotation. Do you think it gives you a boost? No, it gives you a rotation. It's funny. So this is thing. The last things that we need is the last things that we need is the ji kj. And this I, epsilon I, j, k, kk. You see the algebra completely closed. I have tried all combination and it closed. So the algebra is this. This is the algebra of the generator, of the 6th generator of the Lorentz group. and it totally closes. Look, this is the rotation. The commutator is something analog to when you do two things one after another. So you do one rotation and another rotation, and you get a rotation. But look here. You do a boost, then you do another boost, and what you get is a rotation. This is an effect that is called Thomas precession effect, but we will not go into detail of that unless you have just a full course on special relativity. Look here. I do a rotation, then I do a boost, and what I get? I get a boost in another direction, okay? So you see which strange combination you have. Now, how do we build the representation? Because we know only how to build the representation of the Lorentz group, right? Build the Casimir and so on and so forth. First of all, in that table of things, I said first we have to find the Casimir. Which are the Casimir? There are two. I will write them down. So let me write the algebra somewhere. Now, the Casimir here is J squared and then I diagonalize this. There is H bar square, but I put it to 1. H bar can be 1. Don't go on. Why? He gave the right answer. You all together have to do a cooperative work and tell me why it can be 1. Next class I ask you, okay? I don't care that just talk to each other. You don't tell anything, please, okay? Why it can be 1. I put to 1, but people say, come on, it is 1.3 point something 10 to the minus 34 erg per second. But people often put it 1. How they do? Why? You have the answer? Tell me. Not really. Not really. The point is a dimensionful quantity, h bar. So I can go on an exoplanet, and instead of using erg per second, I can use exo-erg per exosecond and make such that that number become 1. Change the unit. You cannot do that with pure number. You understand? You see, we are very much physicists looking for things that are pure number, that don't change with the unit we use. H bar instead, in the normal unit that we use, I don't know, they are called international units, or I don't know, I never remembered that, is either that small number, or we can change the unit and make it 1. But it's not 1 as a number. You should have said, 1 times exo-erg over exosecond, in some unit. Okay? So every dimensionful quantity, you can change the unit and make the number you want. But if I give you a number, 7, and you say, is a number, you have always to say, when they give you a number, remember this, next year you will encounter plenty of this. But this kind of information, they are never given. When they say, oh, this is 1 over 37, what? Apple, eggs, camels, lions, any animals you have in your country, whatever, horses. Or if they say, no, it's a number, okay, fine. Then they don't have to tell you anything else. Otherwise, if they give you a number, they have to give you in which unit is that number, if it is a dimensionful quantity, okay? So remember this important, this is a fundamental thing for physicists. And, you know, I learned at 58 year of age. I should have learned at 18 or your age. That means when they give you numbers, you always to say, it is a number or it is a dimensionful quantity. If it is a dimensionful quantity, to tell that it is 1 over 37, it means nothing. It is 1 over 37 kilometers times tons and divided by hour squared, or it is a number. So we are always searching for numbers, and okay, you understood. Now let's go, here is the Casimir, the operator that commute with everything, all the other. Now let's go here, let me rewrite first the algebra here. Let me rewrite the algebra of the 6 generator. I don't, well, let's put some because I don't use the Einstein notation here. Then I have chi I. And then the last one is ji kj. Okay, this is the algebra. The next question is, and let's write here that the rotation are exponential I alpha eta times j, and that the boost, or a Lorentz transformation, a boost is exponential minus beta mk. There is no I. Let's now go and build the Casimir. Then we stop here. No, well, I tell you one more thing. The two operators that commute with everybody, it's the two Casimir, with all the 6 are these. 1/2 j square plus k square, and this j times k. These two are the two Casimir. So what you do, these commute with all the 6. But you see, they don't belong to the algebra. You see, this is, you do the square. In an algebra, you are not allowed to do the square. You say they belong to the enveloping algebra, but forget, in case some mathematician on the bus going to town tell you, oh, you have studied enveloping algebra. The enveloping algebra of the algebra of generator means when you do the square. You see here, you do the commutator. You never do the square, you do the commutator. The standard operation is the commutator. So if you do the square, you do something that is not in the algebra. In fact, it's in what is called the enveloping algebra. So now you diagonalize these. And you have to put here some numbers that are the eigenvalue. These two numbers will characterize the representation like this number. That you remember if it was 1/2, 1, 3/2, 2, and so on, it characterized the dimension of the representation. The same here, the two numbers characterize the dimension of the representation. But now, let's see how we do it. Because the algebra is rather strange. And we know only how to do things when we have an algebra like the rotation group. Well, what happened is that it's possible to manipulate these kind of things, these operators, and build other operators that have an algebra that is, so this is the algebra, but let's now, this is the Casimir. Let's make the Casimir here. F 1/2 j square plus k square, and g equal j times k. Okay. How do we build the representation? This algebra, well, this is okay, it's the rotation, but this one start mixing the boost with the rotation. This one, the boost and the rotation with the boost. So it is not an algebra that we are familiar with. So we build the following object. Let's build the following operator. A, define 1/2 j plus I k, please. Which one? G, how I found? It's just, this is the second Casimir. So this algebra has 6 generators, differently than a rotation that has 3. And so I expect that there are more. Oh, I found, check it. Do it as an homework. That means this object will commute with all j and k, and the same this one. Okay, so that means, oh, I found this, means I did not find. I can tell you, if you do this, it commutes with all 6 using this algebra. If you do this, it commutes with all of them also. So there are 2 quantities that are linearly independent that commute with the things, and these are called, I expect that I have more. I have 6 generators, after all, 6 parameters and 6 generators, so I expect that I have more Casimir than just. In fact, Lorentz Group is, they say rank 2. I think is rank the name of the thing, but okay. Now, anyhow, this is difficult to build the representation. The representation we know when we have an algebra like this. Can we build an algebra instead of this? Can we build an algebra combining the j and the k that looks like the rotation group? Yes. If you build A and B, 1/2 j minus I j k, then, surprise, these operators that are 3 and 3, defined in this manner, have, look, AI, AJ are I, epsilon I, j, k, AK, sum over k, and BI, BJ is equal I, sum over k, epsilon I, j, k, BK. Epsilon I, j, k I did not say, but it's the totally antisymmetric tensor, you know, the one that is 1 or... And AI and BJ commute. Look, fantastic. I have 2 rotation groups. But there is a difference. J and K were Hermitian. A is not Hermitian. A, if you do his dagger, it goes into B. So these are not Hermitian, but have the algebra of 2 angular momentum. So SO31, people say, oh, is isomorphic to SO3 times SO3. Because this is an SO3 and this is an SO3, right? They say something more, don't take too seriously these things, in the sense that I'm not a mathematician, and I don't want to be actually, but I am trying to convey to you which are the mathematical structure that I know that many of you are more mathematically oriented than physically oriented. It depends on education from country to country. In Italy, for example, I teach in the 3rd year quantum mechanics, and I get students that are not physicists but little mathematicians, and they ask to me, oh, the theorem, how did you prove that theorem? I proved nothing. I mean, they want that I proceed like a mathematician, and I told them, move to mathematics, please. I mean, I don't want to see your face anymore. And I tell them explicitly, I hope you don't have that background, because that background will make you mathematical physicists that are good, nice set of people, but you want to become physicists, right? Most of you. So I don't know which is your background, but let's say if some mathematicians see this and said, oh, come on, it's not like that, it's SU2 times SU2, but I have not defined for you SU2, but I know it's isomorphic modulo something to this. And so when you see this writing, it means the algebra of the Lorentz group is isomorphic to 2 rotation groups, but the A are not Hermitian. So I have to watch out, because when I build a representation here, I use strongly the fact that J was Hermitian. And I use the algebra and the hermiticity. Please, this afternoon, go back and review how you build the representation. Look how much heavily you use the fact that J was Hermitian, okay, to get these numbers, this discrete number, and to get that they are finite, the dimension of the representation. Here we are losing a crucial ingredient, so next time I'll give you the next chapter of this soap opera. Now we will actually be finished almost, okay, but because we don't want to go into special relativity and group theory. We have to do relativistic quantum mechanics. So, by the way, this is the book, Greiner, that I will start using from next time. I will not send, this is the last note I sent to you. This book, there are several copies. This is my own copy that I bought for myself. I write down here, Greiner. And we will do few chapters of this book, Relativistic Quantum Mechanics. Now, if last year I managed at the library buy 3 or 4 copies, if you don't have enough of this, every time I say we will do for sure chapter 1, part of it, not all of it, okay? So if there is not enough copy, just make Xerox of the relative part that each class, I tell you, this is the first 3 sections of chapter 1. You understand what I mean? But they should have, not this year you are many, but they should have at least 3 or 4 copies. And okay.